Okay, so it looks there is more people now on the webinar, so we'll start now. Just as a global rules, you will receive some questions and some polls during the webinar, so you have to answer to them if you want. It's just to ask you a few questions, to get better webinars for next time. So feel free to answer to these questions. And if you have questions to Laurence, you will also be able to actually ask them in the questions part of the GoToWebinar app, which is on your right. You have a small question tab. If you just can, answer your question, ask a question, and I will manage them and I will ask them to Laurence at the end. And so we will actually answer all these questions at the end of the webinar. So don't feel frustrated if we don't answer them in the beginning. We will take all the questions at the end of the webinar. That will be the end of the webinar. So now I will actually, introduce you to Laurence, who is working in Sigfox since a very long time. She will be better to explain you than me about that. She's an amazing radio engineer from our team in Toulouse, and we are very glad to have her on the webinar. And presenting a very interesting topic, which is very important for device makers. So I will leave the floor to Laurence for introducing herself, and then the floors will be hers for presentation. So enjoy the presentation, and if you have questions, please ask them in the question box. So Laurence, it's all yours.
Yes, thank you, Anthony, and good afternoon, ladies and gentlemen. I'm happy to be with you here tonight. I'm always happy to talk about the technology, the good stuff, best practice, whatever. So just for a few words about myself, I'm a radio engineer from a long time ago. I've been doing radio stuff in cellular, in hardware, software, a lot of stuff. Now I've been at Sigfox for a long time now, and I can be described as a wireless system architect. So I build new system feature, I design them, I do some research, and what I do love most about the job I have is that from time to time I have the opportunity to share, to explain. I try to be as simple as I can, so don't hesitate if some things are not very clear. That will be good feedback for me also. So today we've been playing around at Sigfox with a device cookbook for a long time internally, building stuff, different chapters, some stuff very oriented hardware, some stuff oriented system-wise. So because I'm a system person, I will present you the system aspects related to configuring the transmission inside the device to obtain the best performance. Okay, I'm happy you are here and you have decided, obviously, to run the IoT challenge with Sigfox. This is obviously a good choice. And this session is here to help people who are eager to start, who are wondering how to do best, what to select, what are the options, what to tweak, how to obtain best efficiency. Here are recipes to give some good practice and elements of response. Okay, one moment. So why a cookbook? Because cooking is about associating food ingredients in proportions and obtain reasonable, delicious, or nasty dishes in the end, which is to me very much like engineering. Because engineering is manipulating parts, parameters, tools, imagining new things, or trying to reproduce results, and it's really quite similar. So this presentation here and the cookbook principle, it's not about giving you specification or giving boring things or trying to feed you with a one-size-fits-all solution. It's not at all about that. We are here to discuss system balance, to understand what are the parameters available, how to leverage on the benefits for a best communication, how to make smart associations, and to obtain the best solution on the network and to maximize your own connection experience or your own customer's experience. Okay, so I don't have a very long introduction because I think we, all of us here know what we're talking about. Sigfox has the ambition of connecting the physical world, provides a technology, has built networks to facilitate the access to the technology, provide technology bricks, etc. But connecting the physical world to make value out of the data starts with collecting information inside the device and reporting that information over the radio connection to the network. So connecting the physical world is also a matter of managing a good transmission configuration. So there are quite a number of parameters, of ingredients to cook together to build a proper transmission configuration. The most important, they fall in two categories, the protocol options, first of all, the way the transmission, the way the data is transmitted, the way you can configure how it is transmitted exactly. Then you have a second range of ingredients around the radio behavior of your device. So its power class, its ability to radiate in the environment very well, as well as the influence and as well as the variability related to a device operation in the field. And then there is, of course, also optimization margin in the capability of the device. There are some stuff you can do in hardware. And on the other hand, what you're going to get out of this effort is a number of benefits and a balance between a number of benefits which are related to the energy savings, the quality of service, and the cost, mostly. And the complexity also, but it's not mentioned here because here is a very simple aspect. Okay, so there we go. That's the scope of today. We're going to go through several topics. So for each topic, I will provide some concept aspects. So the parameters, let's say, you can play with, you can tweak, and the simple parameter association that provide certain system leverage. Okay, so we will go through first a warm-up part, let's say, a simple one, not the most important not the most important, but something very basic about the protocol that will help understanding some stuff about Sigfox, I hope. Okay, so this will be the traffic model, how to link the efficiency of the traffic model between your use case, the technology, and the system performance that you want to obtain. Then we'll have a part about the ultra-low power mode that you can tweak by configuring the radio transmission. So, and here there's a give and take. It's really a trade-off. So you'll have the information and you have to decide. You make the balance yourself for your application because IoT is not like cell phone, which are supposed to be handheld. IoT devices can be anywhere, underground, top of the buildings, outdoor, in the ground, in rural fields, etc. So it's a lot of various situations that require a lot more flexibility and in the options that can be tweaked inside the devices, okay, to adapt each situation. Then we have a short part to provide you some system aspects regarding the downlink and how to maximize your downlink experience. What is your role as a device maker in the downlink experience? Then we have some, next part is about the device class and how to target the right device class for your use case. And then that's my favorite part because it's the radio part. It's about the field experience, how to maximize for a device that has been designed. You have solved all the issues and designed your device, configured it well, etc. Then you will observe stuff from the field. And the observation that you do from the field experience with the devices that you spread out in operation, you're going to collect observation and see things happen, and some of which are related to pure radio effects. So the understanding of these radio effects, of the variability, will help you manage the maximization of the field experience and the usage of the device in the field. Okay, now the easy one, the traffic model. Okay, so the traffic model is basically the requirement of your use case. Your use case knows, has a requirement regarding what to communicate, how much volume to communicate, how much data, how often, triggered by what event, is it periodic, aperiodic, whatever. This is your stuff, this is your application you drive. Now, this, of course, when it's used over Sigfox protocol, it results into configuration of the library, let's say, of the software, of the embedded software of your device. And it all falls back to how your payload will be managed, the payload of the messages, let's say, the periodicity or, let's say, the triggers of the transmissions. And this has a great impact on energy saving. So the balance for the use case is the protocol options and the use case definition against the energy savings, knowing that there is a constraint, which is regulatory compliance. Okay. So just that everybody starts at the same level. I don't know if you guys all have the information. The construction of the Sigfox frame inside the device by the library is extremely simple and straightforward. So the library is a simple software module, let's say a few kilobytes in size, that manages aggregation of a small protocol overhead inside a binary stream that we call a frame, which is in fact a datagram. So it's a payload plus a small payload over a small protocol overhead and physical markers for the physical transport over the air. And the library produces a self-contained datagram, which means that the network, the Sigfox network, anywhere can detect a frame from that single datagram, identify the issuer, identify the customer, provide a status on the authenticity, verify that the signal has not been corrupted over the air, and can then process the content, the sensor data, let's say the object data, to the object owner or the guys who operate the device. So far so good, very simple. Now this property of the Sigfox datagram to be being self-contained is extremely interesting because it confers the really low power aspect to the transmission, and it also provides an energy budget that is extremely predictable for you to manage, which means that you know your throughput in terms of number of bytes or dozens or hundreds of bytes per day, and you are able very easily with a proportionality rule to predict your energy budget. Knowing that, what do we mean by low power? Of course, we are ultra narrowband, so yes, but the energy budget per message falls down to a joule to a fifth of a joule, just to give an order of magnitude. Alors, of course, the transmission is a little bit long because we are at small bit rates for ultra narrowband modulation. But it's very interesting because it allows extremely high energy efficiency at low throughput. Okay, so you probably know that Sigfox is classified among the low throughput network. Now, what does it mean, low throughput network? It means that because we pay a fixed protocol overhead per datagram, so per transaction, in fact, we have a fixed efficiency. So the ratio, we have a fixed energy efficiency. So the payload the ratio payload over overhead is constant, whatever the device throughput. Of course, other technologies, especially those who use negotiation and allocation of resource, are very different. The device pays a lot of penalty in terms of protocol overhead to initiate the communication. So there is a first phase which is consuming a lot of protocol overhead, a lot of energy, let's say, and doesn't transmit any data. And then there is a second phase in which the data throughput is very high and the protocol overhead associated is very low. Of course, this is very efficient for and very energy efficient for high throughput, but for low throughput system, it doesn't make sense because the penalty in terms of protocol overhead and battery is a killer. Okay, so this is why we say this is why we are classified as low throughput network. Our energy efficiency is really maximal at low throughput, yes, but how low is this throughput at which Sigfox is the most efficient? Alors, I took let's say a simple figure, simple to remember. Let's say, so the big picture is that Sigfox is optimal in energy efficiency below 1 kilobyte per day transmissions. 1 kilobyte per day is already very high to me, and I will explain why later. So now you can imagine that you say, okay, well, she tells me Sigfox is efficient below 1 kilobyte per day, so I have 5 kilobytes per day, then Sigfox is not for me. And that's not really true, because above 1 kilobyte per day throughput requirement for a device, you will the energy efficiency of the transmission part will be less efficient energetically, but you will still have access to all the other ultra-narrowband benefits. And these are namely range and so the long range and the penetration ability due to the very large link budget. So penetration ability, I mean indoor, in buildings, in difficult situations, underground, etc. I mean the interference resistance, and I mean also scalability. Okay, so these are all advantages of ultra narrowband that can be more important for you in terms of systems than energy efficiency. But otherwise, you have to decide. Okay, the most important point about high throughput implementation with Sigfox is that at some point you have to think about the regulation compliance. Okay, the conformance to the local regulation requirements is mandatory if you want to commercialize a product using unlicensed spectrum. And regarding the throughput, the ETSI, so the Europe and ETSI affiliated countries, so some of the African countries, Europe and some of the Middle East, the 1% duty cycle hour-based requirement in the hour operated band induces, let's say, a rounded value, 5 kilobytes per day throughput, maximum, with an hour-based constraint, which is usually the biggest constraint is not the daily throughput, but the hourly throughput. Okay, in the other spaces that we operate, either under FCC and affiliate countries or Arab and Korea countries, the constraint is not so hard, let's say, and usually is indirect. So I won't mention in here. But is it really a constraint? As I said, the low throughput networks, why are there low throughput networks? There are low throughut networks and solutions and technologies like Sigfox because there really is a need for extremely low throughput. So I'm a network administrator here. I monitor for my leisure. It's not my function in the company. But I survey what happens on the network. And this week I have refreshed the data for this presentation. But it's very stable compared to 6 months or a year ago. And what I see on the network, we have about several tens of millions of transactions in a day. what I can see is that 50% of this traffic uses less than of the devices using the resource use less than 10 bytes per day. Okay, why is this important? It shows you that in fact there is a natural usage of the technology for the solutions that have no other choice, which are really the solution with ultra low throughput. Okay, then there is about 50% of the solution that use more than 10 bytes per day, and this is also good. And what is noticeable is that there is 1% of the devices, it's not traffic here, it's devices that use more than 1 kilobyte per day, which means that there is really a solution for the guys who are not so energy constrained, but that need to benefit from the penetration, the interference protection, scalability, etc. So there is space for a very different set of constraints to build a Sigfox solution. So you have to pick yours, because your set of constraints in terms of the benefits you want to get over the air, what is your dominant constraint, will result in a very different system balance for every single solution. Okay. This one is a bit anecdotic, but it's one of the details that a lot of people don't know, is that in fact you can, and you should, optimize the usage of your datagrams, because in Sigfox you can select the payload length. So let's say the library API allows you to select freely the payload length between 0 and 12 bytes. But in fact, behind this selection is a fixed, is discrete datagram length, which means that if you, let's say, I'll give you an example, I will not read through the table. If you have to report sensor values, aggregated sensor values, and they take 5 bytes, if you contact the Sigfox library inside the device and request for a 5-byte payload transmission, in fact, the datagram will build an 8-byte payload transmission, and with your 5 bytes and 3 bytes padding. So what it means is that in this situation, if you have chosen 5 bytes, then you have lost 20% energy for this specific transmission. 20% energy is low compared to the paragraphs that are coming next, but it's still important. It's still worth thinking, how can I adjust exactly the payload size that I have to the datagram size that the Sigfox protocol provides. Then you have solution. You can aggregate data, for example, take several bits of data of different types and generate an 8-byte data instead of, let's say, several chunks, several 5-byte chunks. I don't know. There are a lot of solutions there. So, as a little summary about the traffic model, we've seen a little some various aspects. The most important stuff when you build a traffic model is to know well and manage and categorize, classify your data, because they will not be processed in the same way. To me, a lot of applications, but not all of them, maybe some applications are managing critical and urgent reports, such as alarms. And for critical and urgent data to transmit, the immediate reporting requirement offers very small space to optimization. So if you have that, okay, it's just life. Now, if you have the other cases, like non-urgent data to transmit, may it be critic or non-critic, you can probably delay the transmission and aggregate with other data chunks. In this way, you will maximize the ratio, the energy efficiency, because you will maximize the ratio in terms of protocol, Sigfox protocol overhead versus your data over your data amount. Okay, So aggregation maximizes energy efficiency. And there is quite a lot of energy to gain in thinking this aspect well from the start. Okay. Some of our partners even go further and manage their payload with a kind of applicative coding. In fact, this is a form of custom compression, but it doesn't appear like this when you design. When you design, you say, okay, I have several kinds of data, and one of the data reports I do is very often. I do it very often, and there is little change. But it eats up, I don't know, 5 bytes payload. If you have non-critique data associated to a recurring request to the network, then there's a way to say, okay, I'm gonna just provide an index referring to the fact that this message should be 5 byte payload, but I'm saying, okay, this is maybe just an alarm case that I want to signify. This one is recurring, so I'm going to send an ultra short frame with, why not, no payload, saying, okay, this is just an alarm, okay? And the applicative system inside the customer servers detects and decodes this applicative coding, and this allows really a form of compression over of the transport over the air. Okay, so this was the first part. So we've seen some simple ways, methods to gain some energy with a reasonable management of your traffic model. Now there is more. We have more protocol options that allow to drag down the energy savings, drag down deeper the energy savings. But they are a trade-off, okay? It means that we have a protocol option when it's combined, when it is available, and which is available, and in certain link quality condition, you can play with it and gain the energy savings without sacrificing the quality of service. Okay, the energy savings in this case are about 60%. Okay, so you drop down, so you divide your energy budget by a factor 3. It goes down to 80 millijoules per message in that case. So for you to understand this ultra low power mode, we have to step back to understand Sigfox link management reliability, which I call here quality of service, but the quality of service related to the radio interface. If you are familiar with the Sigfox technology, you probably already know this, but and not what's coming next, so little patience. So the way we have engineered the quality of service in Sigfox on top of random access method on the air interface is as followed. We have, we have calculated, we have models for the point-to-point success rate of radio access in the radio medium and the shared spectrum radio medium. The figures are not very good, of course. You're looking at 60% success rate for a point-to-point transaction in, let's say, between one message issuer and a message receiver. So really point-to-point mode. Now, in order to offer quality of service to our customers, we have built a diversity mechanism, which is in fact a way to virtually generate multiple links in the system. Instead of a single device to network link, we have now a device generating multiple events to several network terminals at different locations in space, receiving the radio blocks generated by the device. Okay, so in other words, this is visible here on the picture. One device for one data payload will generate let's say in this case here, with 2 base stations, 6 potential receive occurrence in the network. Okay, so one transaction, 6 virtual transaction occurrence, it means that we have a pure statistical leverage with the diversity that increases reliability with an exponential low function. So I have noted this down here for the record. So there's a theory behind it. We have papers that we can share if necessary. But remember the idea, the quality of service of Sigfox is really a matter of the diversity, of engineering a system to overcome the collision mechanism in the pure ALOA conditions. Okay. Now, we've seen, let's say, the bottom-up approach, okay? Time diversity and frequency diversity on the device, spatial diversity on the network, but, well, diversity is a global factor. Diversity is not only time and spatial, but is the sum of both. So what if now I'm not looking at bottom-up, but at top-down, and I'm saying, okay, I have a global factor of diversity to provide the quality of service to customer, and I mutualize this diversity. I try some other stuff. So here I'm representing an example with 2 configurations. One device in one case is in the standard low power mode, let's say, generating multiple frames. And this one is in sparse network conditions. So the quality of service in the left-hand configuration is mostly driven by the device contribution. So in rural condition, this is typically what happens. The network is sparse because the device density in rural area is low. And the link quality, because there is no city shadowing, etc., is probably good. So the quality of service contribution related to the diversity is mostly from the device. But within cities, I have a lot of base stations available because I have a lot of devices. I want a lot of quality of service. So we've made cities with very good coverage and a lot of diversity. Now, if I want to have a diversity of 3, well, I can try to do it based on the network contribution only and spare the energy inside the device. Okay, so I have mutualized, in this case, the diversity factors, and I spare the device contribution because it is endorsed by the network. So on the left hand, we have a situation where we're looking at a diversity factor of 3, which is endorsed by the device. This is the classical low power mode. And on the right-hand side, I have the diversity factor is contributed only by the network. This is only spatial diversity. This is the ultra low power mode because the device contribution now to diversity is removed. Alors, I don't know if you probably are skeptical. The both solutions are more or less equivalent. But in fact, we've built some models that show that there is a slight difference because spatial diversity is a stronger leverage on quality of service than time diversity. Why? This is very simple. So it's because the time diversity overloads the resource. So when you overload the resources, it's as if you were having more devices communicating. So the overall contention increases. Okay, whereas the spatial diversity is purely passive from the radio interface standpoint. So it unloads somehow the resource, so it provides better conditions for the whole population of devices. But okay, this is a modeling in equivalent radio link conditions, just the network conditions are different. The number of base stations is different. Now, okay, this is explained with the ends. Now, this ultra low power mode, can you use it? So, yes, of course you can use it. All the options that are with Sigfox you can use. You can try them, see if it works for you. But there are, we have here a simple rule to a simple parameter association to understand if your application is eligible or not. So in DID, the system constraints of your applications can be of several types. Okay? Most of our applications are energy constrained, but some are not. Most of the applications also belong to specific link conditions. The indoor, for example, or underground is a specific link condition. And you may have critical data to send, which is why I mentioned reliability. Or you may have a portion of your data may not have a high reliability requirement. You may lose one frame every once in a while and you don't care. You also have something related to the periodicity of your message. If you have a high periodicity of message and a little bit of application coding, then you can probably accept a few frames lost, let's say. But this is the trade-off. Okay, so the ultra low power, if you need it because of your energy constraint in your application, for example, if you are doing energy harvesting, this is a good solution, but you have to know that there is potentially an impact if you are not in good link conditions. So ultra low power is good for applications that are in good link conditions, that have high periodicity and that have low data criticity. The classic low power implementation, on the other hand, is available for all still, and is preferred, of course, if you have difficult link conditions. For underground water metering, I would not go for ultra low power. I will find some other energy solution, but I will need still the quality of service benefit of the classic low power system. Okay, so these are, let's say, how the complexity develops for the two, and the relationships develop for the two options. Now, for your application in clear, what it means is that because there are areas and situations better covered than dumb, then you can identify very quickly if you are eligible or not. For example, cities are densely covered, very well covered. Outdoor situations, may it be cities, suburbs, or even further, small cities, etc., they are also naturally well covered. High floors or rooftop situation is naturally well covered in terms of radio, so they will transition very easily to ultra low power. Okay, whereas, for example, solutions that require that have hardened radio conditions, such as indoor, deep indoor, or rural, will probably have to remain to the classical low power solution, which is a better compromise in terms of system to obtain the best balance between quality of service, link quality, and energy. Now, there are some products, of course, for which the radio conditions are not known. So they are, depending on the main constraint of the application, you can go for either one of the solution, or you can even build an adaptive scheme. Let's say test the network link quality and select how you will manage the coming communication. Okay, a few words about the downlink. I was not supposed to have that one here, but I added it at the last moment. The reliability of the link in downlink is very different than uplink. In uplink, most of the reliability of the link is endorsed by the network. The device has a responsibility also, because now it can play with the low power or ultra low power mode. Both of them is a way to balance reliability with current drain and quality of service. Now in downlink, it's very different, because in downlink, you know the way it works with Sigfox. It's on-demand polling of the device for response, okay, which is very good because in terms of energy efficiency and spectrum efficiency, it works very well. Now, low-cost objects of IoT have receivers, and the problem of the reliability of the link is that it always depends on the receiver. So the communication, because the communication reliability is a parameter of the receiver, the reliability of your perception of the downlink service depends on your own design of your device receiver. So what can happen, in fact? What can happen is that there are some hardware, let's say hardware radio parameters, which I state here, the linearity and the selectivity, which make your receiver sensitive to strong signals passing by, and that can potentially generate dissent. Okay, but it may happen or it may not happen. It depends on the conditions your device will be in. So let me finish the one. In fact, if your device is in exposed conditions, the ones that we reviewed in the previous slide, exposed conditions mean rooftop, outdoor, etc., it has more chances to be in an environment where there will be strong radio signals. So it has more chances to experience a slight change in its experience of the reliability of the downlink. So if your device, in other words, go into that kind of condition, then you have to think about building a filter front-end adjunct, so building a filter with a small low noise amplifier to increase the selectivity of your device and protect the device against its radio environment. But this is not mandatory. The large majority of devices are supposed to be in buildings, etc., and they are not exposed to hard radio conditions. Now, the first aspect, I went too fast to the second one. The first aspect is also a downlink feature is good and available and is useful because you need to update your device with parameters from time to time, but it eats up an energy. So use it when you need it, but build the value out of it because it will take a portion of your energy budget. So you have to use your energy budget wisely. No, if you don't need, for example, don't acknowledge, don't request the network to acknowledge an uplink message reception every time if your message was not extremely critical, because you would waste the energy. Managing acknowledgement is possible, of course, for very critical data or getting network link information every once in a while, but otherwise you can spare the energy budget and use it in another way. Okay, now, but just a few more words, which is interesting is that the fact that your receiver in a device is imperfect and might change your own perception of the downlink experience is something you can use also to detect the dissent phenomenon. So either detect the presence of a jammer or a blocker or something not normal in the environment of the device. So this is something that can be useful, and because your device will generate, let's say, signal artifacts in the presence of strong signals, this is something you can use also to build value out of it in the back end of your processing and application chain. Okay, a few words about the device class. You probably know the device class because of the makers, they cannot understand why we have device class and what for and how it works. And everybody wants to go to class 0, but it's not that simple. Class 0 is for me the reference, but it's not the one-size-fits-all solution. Because, well, of course, the device class is quantifies how well your device radiates. So it quantifies the footprint of your family of devices, which is pretty fair. The way it has been classified is that each time you go up a class, you lose 25% reach, you lose 5 dB, in other words, so you lose about 25% reach from the reference. Okay, so you drop severely in class 3, for example, you have dropped severely to 10% of the class 0 footprint. Well, so far, so good. Now, if you look at it more closely, in fact, if you use the same antenna to make a class 0 device and a class 1 device, then the class 1 device will have a lower footprint, but will have 50% energy savings, which means that the class and the radiated power is really a way to drag down your energy budget. Okay, and of course, the energy budget means smaller battery, longer autonomy, lower cost, because the battery is smaller. The battery is cost a lot of money, so smaller battery, less money for the battery, and also a smaller form factor. So, of course, you have something to pay for it, but in exchange, you gain other benefits. So here it's a trade-off that is in your hands to manage, and so that you can select your class, the class of your devices, of your target devices, so depending on your dominant constraint in the system. Again, we are here in the same situation as before. Everything that is well covered and densely covered, densely serviced by the deployed commercial networks with Sigfox are favorable to implementing higher class 1 and 2, even 3 in some very specific situations. Okay, everything that is very sensitive to battery as energy harvesting can sacrifice maybe also a little bit of the device footprint to get the energy harvesting benefit. Okay, because there is a large benefit in doing this. For all the rest, everything that is less not well serviced because of the screening, RF screening conditions and shadowing, mobility, rural condition, etc., you certainly are going to prefer stick with a class 0 target. Okay, and sooner or later, of course, adaptive scheme are going to emerge. I still have in mind to design one, but I have no time, unfortunately. Alors, now, if you have followed up to this point, you probably have a question. You say, okay, there are several ways to gain energy. There is this ultra low power mode, which costs a little bit in quality of service, and there is this targeting an higher class for a device, which is somehow reducing the footprint. So what should I do? Which one is better? Alors, here again, I have a technical answer, but there's not only one answer. There's one answer for one use case, which means that, okay, the benefit of the diversity in Sigfox, I only tackled one aspect in the previous slide. In fact, the benefit of the diversity is extremely large. So I would rather maintain the same link budget for a device, the same link budget, sorry, my voice is a bit broken by now. I would always prefer, as a radio engineer, maintain the same link budget and reduce and let's say cut off the time diversity. So I would go, if I need the energy budget, I will go for the ultra low power mode, which is a protocol implementation rather than class 2. But this will have less impact on battery, but this will allow to maintain the diversity in the system because the footprint of my device will remain. But you can have a different approach and different justification to say, okay, diversity is good, but I need more. I need to gain more energy because my application is really sustains very hard energy constraints. So, and this is a good reason to try something else. Okay, this is a good reason to go for a class 1 or a class 2. Okay. I hope you followed me up to this point. And now we have the radio part. If we've not too late, I'd say we're fine. I think we're just in time. So that's my preferred stuff. Because once your radio is designed, we've not seen all the details of the cookbook design chapters. This will be later. But this is not the most important, because some of you guys have probably bought some devices off the shelf already, or have designed their own devices and tried to use them in live. And you probably have experienced that once the device is designed, you have made the choices for the traffic model, for the class, for a lot of stuff, for the system parameters, and then the work is not over. Because in the real life condition of devices, you experience real radio channel conditions, and they cause variability in the service experience, in the link experience. Alors, all the variability is not related to the radio, because part of it can also be related to the manufacturing stability, but this is something that we will not discuss here. Manufacturing is really, really a huge challenge for IoT, but this is a topic for later. We will focus here on the radio variabilities. The radio variabilities, they divide into two, let's say, two branches. Everything that's related to the device placement and the antenna detuning, which is a huge cause of reduced service experience in the field. And on the other hand, you have everything that is related to normal channel behavior, radio behavior, so shadowing, multipass, fading, etc. So now, all the elements that I have cited, they have a link budget impact, and the link budget impact is a service experience impact, and in the end, the service experience impact is cost impact for you and for Sigfox, for all of us. This is why it's important for you to understand the variability cause and think in advance on how your devices will be used in the field in order to avoid the perception of variability. Okay, so there are things to do to design your devices to avoid variability, and there are things to write and implement, let's say, in simple stuff to not to fall into the pitfalls, okay, of radio. Alors, the first part, if you guys follow the webinars of adoption, I think last year, maybe it was 2 years ago, my antennist colleague has done a very good webinar and also a video. There's a video which explains the detuning of antenna. Alors, back then, the series of the webinar, maybe you've not seen it because you're not interested in antenna design, but in fact, once the antenna, the antenna has to be designed for its final usage conditions. And this is very important. And if you use a device in a different conditions than it was designed for, in that case, you will probably suffer from antenna detuning. What is antenna detuning? Alors, I'm not saying detuning here in terms of frequency. I'm saying detuning in terms of modifying drastically the behavior of your antenna. In the illustration on this slide, you have a view of the antenna of the Sensit, which has a clean radiation pattern, quite good in the open space. But then the next simulation view on the right-hand side shows what happens if you put the Sensit on a metal table in a atelier, in a lab or whatever. So, or in a wall with metal under it, whatever. This is the extreme condition, I agree. But in this case, it shows that a product that is radiating well, that has been classified 0 as a reference performance in the Sigfox network, placed into specific condition, will radiate less than 0.25% of the initial energy. And there's a huge penalty in the link budget related to the antenna detuning. So the quality of service drop in that case is just enormous. And of course, it's an enormous also energy waste, because everything that is not radiated stays within the device. Okay. So, but it stays, but it, let's say it can damage. we are 25 milliwatt, it's not going to damage, but the idea is that it stays within the device will heat up, become older more quickly, etc. So this problem is really worth understanding and taking a look at it. And for your product, think about its final usage condition to design your antenna for the placement it is intended to be in the house or whatever, in an office or in a factory or whatever. And also give a recommendation to the users in the datasheet so that they use the devices as you have planned, so that they obtain the performance, they have a good experience by placing the device in the conditions that you have designed for them. Okay, so this is really an important cause of, let's say, not well understood and not well managed variability of the link. Now, regarding shadowing, I've taken the example of indoor. I could have taken city, but I've taken the example of indoor. The footprint of a device is going to vary largely in situations that we describe simply in human words. Let's say city or indoor describe a lot of different situations in terms of radio. Okay, I took the example of indoor here and said, okay, we have a reference device footprint outdoor in class 0. And I have represented next what happens when you place it underground. Underground, in a cellar of a house, you will be more or less around between 25 and 35 dB, which means that there is 1,000, so 0.1% of the initial device energy that goes out of the house. Okay, this is just enormous. Now, but the opposite situation is also true. In fact, if you place a class 0 device on top of the building, you will have the impression to have better, much better link quality than at ground level. It's not that your device radiates more. In this condition, it has more favorable propagation conditions, and some of the usually present absorptions in city condition, let's say at ground level, they don't exist in the higher floors. Okay. So there are, of course, a lot of statistics and a lot of study about shadowing, indoor behavior, etc., or about city behavior, because city is the same kind of problematics as indoor in terms of shadowing. And there, again, to design a good experience for your customers and for yourself, for your application, you have to know exactly what your device is supposed to do and where it is supposed to operate. Okay? In the case no precaution is taken to manage the shadowing and the operational zones for the device, the condition, etc., again, there's a service impact, and in the end, that's cost. Alors, that's probably my favorite. So, mobility raises a lot of questions in terms of in the IoT, because there are some physics related to the mobility of radio devices, which are pretty simple, but they are quite, alors, not difficult, but they require some quite of engineering to overcome. Now, not talking about Sigfox, and more generally about radio system, the most famous effect of mobility on propagation signal, so wavy phenomenon, is Doppler. The well-known police. I will not manage. I don't remember the translation in English. The most famous is Doppler, let's say, but we have a DNA in Sigfox. We've built low-cost solution for drifting devices, so we are insensitive to Doppler. Yeah, I forgot that far. So Sigfox has natively built Doppler resistance, Doppler shift, and Doppler drift, which means that for us, there's no impact. there's impact for cellular phones because cellular phones have to maintain synchronization, whatever. So when they move, synchronization flies away. So they have to compensate, but we don't have that problem. There's a second problem that has appeared with the wideband systems, cellular system or military wideband systems, is that when the symbol rate is extremely high, in fact, in mobility, there starts to be inter-symbol interference. With Sigfox, we have ultra-narrowband. Our symbols are extremely long. Inter-symbol interference in mobility doesn't exist in the terrestrial, let's say, conditions. Okay. Now, what is applicable, what applies really, what is visible, the effects of physics that are visible on the Sigfox signals in mobility is fading due to the pure geometry, alors recombination of the multiple paths, the multiple geometric paths. What is it is that when your object is moving, the signal, the radio wave it generates propagates in various directions and bounces on obstacles and generates reflected and diffracted waves that, in the end, recombine. Recombine at some point in space where a base station is located. So the combination in phase and out of phase of a multiplicity of paths generates positive, constructive interference or negative, destructive interference. When the object is moving, these conditions of destructive or constructive changes very fast. So the wave form that I've represented on the right is the amplitude of a signal of a moving object with a fixed reception point and represents the successive constructive and destructive combination of the radio energy. Okay, so there's no way to avoid the fading phenomenon because it's pure geometry. It's really pure low-level physics. Okay, the fading is a statistical stuff also because it it can be represented in statistics because it all derives from an equation and the Maxwell equation and the environment around us, but it describes in terms of probability. And in fact, there is, let's say, 99% of the, in 99.9% of the cases under fading, the variations of signals will contain between 20 dB. But it means that in order to be under contact of a base station in fading condition, you have to be in line of sight or within a 20 dB attenuation range of the network. Okay. So how to avoid this? Either you manage the behavior of your device and say, I assume that my traffic, let's say, will incur a drop in a signal reception rate. So I send more data, so I spend more energy, but mobility, there is no way to, there are reasons why you have to spend more energy in mobility, is to place more reliability on the signal. Okay, up. Alors, multipass is not only visible in mobility. Multipass also happens around us all the time, also happens in static, also happens in your microwave oven, let's say. No, it's not exactly the same stuff, but it's a recombination, a positive and destructive recombination of waves and energy generates a kind of odd points, which were on the previous slide, the top part of the signal, and cold points, which are the lower parts. So in static, it can be very easily shown in a color grade. Here it's a view of a cavity, but in our environment, it's the same. And in fact, in close, because the spacing between positive combination location and negative combination location is associated with the wavelength at 900 megahertz. Let's say you will have in a very small zone, you will have regarding to the multipass combination, some hot points, let's say, and some cold points. Alors, the impact is small when you are not in mobility, because it's residual multipass behavior. But you can have up to 3, 5, 6 dB locally. So you can, for static objects, which are at the limit of the network, you can still try to find if there is an optimal locally when needed. Now, is there more variability? Which means that, is there magic in radio? No, there is no magic in radio. It's very deterministic, so far as we have observed, at least. It's a lot of statistics, because the deterministic part of the radio is so much complex that we express usually it in statistics. So once an object is installed and static, you should not experience residual variability. Alors, what you will see is that the environment around your object, so the cars in the streets, the doors in a building, and or the windows that are open or closed, etc., are going to generate small variation in the geometric multipass conditions. So there will be a form of channel flickering, scintillement, flickering, glittering, or I don't know how to express it. So the channel changes slightly from one moment to the other due to the environment changing, and this generates a very small variation. Let's say 2, 3, sometimes 4 dB locally. Okay, but if you experience more, something goes wrong, probably with the device, or the device is being moved. Why not? By someone that has stolen it. Why not? But there is no other, there is no reason related to the radio of the physics of radio. Okay, I think we're almost done. I hope you are now ready to design your own transmission configuration. You did a good job, I hope. Based on your use case requirement, mostly. You have a lot of parameters available. You have a lot of parameters that you can associate together to make a good combination in terms of energy, quality of service, and cost in your device. Now, okay, this is all in your hands, and there are no mystery. There are association of parameters is simple, but resolving the problem of your own set of constraints is not easy. I hope this helps. So we'll be ready for questions.
Yeah, thanks a lot, Laurence. So it's Anthony again. So what we can do is we'll take the question in a, let's say, ordered method. So I just see that Stéphane Driussi, by the way, from the company Identic, I think maybe you know them, Laurence, is thanking you for the presentation, by the way, because he has to leave, but he wanted to thank you. So
okay.
Thank you, Laurence, for that. That's from Stéphane.
Welcome.
And now I'm going to go back in the order way for the questions. So it was a question first from Alessandro Morales asking if Sigfox was working in both modes, what he called ultra low power and classical low power. So I don't know what it meant, but I guess you do.
Yes, the choice of the mode, let's say, is your responsibility. In fact, what we offer is we support both. So we support both. You can download the Sigfox library today. It supports both. So if you have an old Sigfox library, it has still only the classical low power mode. Now, the library that have been released for a few months support both modes, and the network support both modes. You just have to make sure that you when you select one of the mode, it corresponds to the system balance that you want for your device. Okay, because if you come to me and tell me, okay, I'm building water metering for New York, let's say, solution, and I want to go ultra low power mode, I will tell you, are you sure it's really a good solution? Because water metering, when it's a big city, is sometimes underground, and underground in big city is really extremely hard radio conditions. So for that kind of application, I would advise go for the standard low power. But this is a solution that you have to appropriate for your application. See if it fits your need. What we offer is the options. We offer the options, and we offer you the choice to take it if it fits your application need, or have to take one or the other depending on your application need. Okay.
Yeah, thanks. So we'll go to the second question. There's actually a question about coverage. So Alvaro is asking us, he has an example in islands where there is no internet, no mobile coverage. Can Sigfox work?
Alors, I think we have an operator in Ireland, so I would
my
say
English accent. Highland, like not Ireland, but Highland, like High. So it's like a remote area. Where the question is in a complete remote area, can Sigfox work? I'll take an example like Zimbabwe, for example, because I know it. I know a bit some example.
Okay. Alors Zimbabwe. So I think we have several base stations in Zimbabwe. So it will work in the area around base stations, but there is no miracle in physics. So Sigfox offers a very large link budget, which is around 163 dB, which derives into coverage zones that are really huge. But if you have no operator in a highland or in a rural area, in an island area, then it probably is not serviced. Now, what we do usually is that we provide service map, or our local operator provides service maps so that you can assess if your target region is serviced or not. Because, for example, I do trekking almost every weekend in Les Pyrénées, and Les Pyrénées have this particularity that there are mountains with very steep valleys. They are not well oriented. It's really a mess, let's say. And you get coverages on the top of the mountains, in some places inside the valleys even, but not everywhere. But there's no miracle. Each time you may have an extremely large link budget, you cannot go beyond the laws of physics. So at some point, the signals are too low and they can no longer be picked up. So if you have no base station 300 kilometers around you, let's say, you are sure to have no service, at least until we have satellite service available. But it's not yet available, let's say.
Yeah, thanks, Laurence. The next question was about security. Is Sigfox hackable? Because it's one of the major worries in IoT.
Alors, the scientific response is there is nothing that is not hackable. So now it's all a matter of how much energy you want to put into it. So what I would say is, so again, this is a technical response. This is not marketing, whatever. So it takes a lot of energy to hack Sigfox, but I cannot say it's impossible, because nothing is impossible except if you ask me, is teleportation possible? I will respond in the status of let's say the current scientific knowledge. Teleportation is not possible, but hacking a wireless system in the current state of the scientific knowledge, I don't think, I mean, and if you have an enormous amount of engineering resource and power available, then you can overwhelm, you can hack any system. So this is a scientific response. It's just difficult to hack Sigfox, but
yeah, thanks, Laurence, for that. It's always a tricky question to answer. So Angel is asking where he can find the Sigfox library, and I'm going to answer that directly.
yes.
If you go to build.sigfox.com, you will actually find the library. You have to go on the menu, and I will do it live just to show you. I mean, just to explain you. You go to build, you go to Sigfox offer, and you have the protocol library for devices. So that's where you can find it. You will not be able to download it as it is. You will have to file a verified certification to download it. But this is a place to start with your journey to find the library. So the next question was from Alvaro. What about the advantages compared to LoRa? So what is Sigfox advantages compared to LoRa?
There are so many of them. Where do you want me to start? Okay.
No, yeah, maybe yeah, not on the no, because as I always do presentation, I get the same question every time as well. We could spend 2 hours regarding that, I guess. So maybe let's say the two main points, the two main difference, one business and one technical.
Yes. Okay. To me, the major difference is that LoRa is a good solution for proximity private network because they can operate the modes that are, I think, efficient, like SF7, but there is no way on a commercial network it's going to be scalable. So to me, there's a real, the LoRa technology as a market, to me, a real one in which they are good. This is private network, proximity network, but they want to compete with us in wide area network. And I think their SF12, what I've heard of their SF12 operation in the field is that it's not scalable. It's not resistant to interference. So it's just not really a competitor to me in terms of they position themselves as a competitor, but they are not competing in the LPWA. So I'm sorry, it's very direct, but I'm not going to dissert for hours. I think it can work well, and I think it's very attractive to, let's say, hackers because they have tiny here tits and bits that you can play with and obtain something to play with easily. This may not be the case with Sigfox, unfortunately. But Sigfox is simpler in terms of implementation. It's less pleasure for hackers to play with because it's so simple. So you have less stuff to play with, unfortunately. I'm sorry about that. But our solution is simpler and it makes it more powerful. And in wide area range, it is scalable. It is very resistant to interference. So
thanks. I guess that's exactly what I say when I saw. At least I'm reassured that I have the same speech when I do public talking. So.
Okay,
Thanks,
cool.
Laurence.
Without concerting.
No. But, that's just really nice. We have another question. I mean, so we'll take two more questions and then we'll be set. So one question from Alvaro again was, how much time can a battery long? How much time you can actually go on a full battery regarding with a device?
Alors, well, this is okay. Here again, it depends from a lot of parameters. So the parameters at stake here for battery life is, of course, the size and the energy in the battery. But let's say you have a fixed, you're looking for a whatever battery, which is maybe 1,500 milliamp hour, something like that. What will make the difference is two things: your traffic model, of course, but also the management of the standby current of the radio and of the device. So if you have a AAA battery for a standard device, no special care, whatever, and an average traffic model of, let's say, 10 frames per day, that's about 100 bytes per day, something like that. You're going to be looking without optimization at something between, I don't know, maybe 10 months to a year. But this is not satisfactory from an engineering perspective because you can do very much. And what is extremely important is the managing the standby current and the sleep modes of your internal systems. And every damn 100 nanoamps will cost you days and weeks of autonomy less. So if you're looking at really something like a year battery life, it's going to be easy. Now, if you're looking at 10 years, that's possible, but that's going to be engineering, a good engineering of your hardware. Okay, so this is big picture.
Yeah, so thanks. And the last question was about, it's more a question, maybe a general question, is you talked about application coding. Are there good examples or repos that people can learn from?
Maybe you have some, Anthony. I have
Yeah.
some because I have had access to solution of our partners that have done that, but I cannot disclose it.
Yeah, I do. James, actually, if you go on the GitHub of Sigfox, so directly, if you go on github.com and you go on the Sigfox GitHub, there is like a lot of examples, and we try to update it as much as possible. You go on our on our GitHub, sorry, and you'll find a lot of examples, with PHP, with a lot of stuff. So we try to get as much example as possible there regarding how to use downlink, how to use uplink, how to play with different technologies. That's what we try to do. So yes, there is a lot of examples, and I really invite you to type. Even you can also go on the disk91.com, which is a famous blog post from one of our ambassadors, where he explains lots of how you can actually optimize your application regarding how much you can save energy, etc. So I would really advise you to go on our own GitHub at Sigfox and both on disk, so disk91.com, which is very, very useful for Sigfox. So that would be my advice. Yeah, and so okay, last question, and just very, very last from Alvaro is Sigfox does not need internet because it's connected through satellites. So this is a tricky question because right now our base stations they are connected to internet as well. Most of our base stations have DSL powered internet. That's how major of our base station work. Some of them have 3G as well, so they need to be connected to internet, so both either with DSL or 3G, or some of them are connected with satellite backhaul. But you don't send a Sigfox message directly to a satellite. You send the Sigfox message to a base station, which is itself connected to internet with a satellite connection. This is very different. So be careful not to mix stuff. We've announced some stuff to work with satellites, but this is something very coming in the future, and you will hear about it, soon or in a couple of months. You'll see. But as of today, the Sigfox protocol, you always send a message from your device to a base station connected to internet with either DSL, 3G, or satellite connection. So sorry, Laurence, I answered it directly because the question actually was so long.
Okay.
I didn't want it to have to repeat. But yeah, so Alvaro, I really, you should listen to our Sigfox Connect event in the near future, 24 and 25th of October. So from that, I would say we will wrap it up. So thanks, Laurence, for your intervention. Of course, we'll send the PowerPoint, etc., as a video because we were recording this session. will be available after that. If you have more questions, we have a Slack community where you can ask more questions. It's a Sigfox builders community, so you just have to go on build.sigfox.com and you will find the address of our Slack community, and I will really invite you to do that. And yeah, I hope that we can see you in the next webinar, which is in a couple of days, I guess. So see you there, and thanks Laurence again.
You're welcome. Thank you for attending, all of you guys.